Assalamu alaikum. Dear viewers, have you ever wondered where the energy that powers your daily life comes from? Let's take a moment to delve into that question. Powering our world is an intricate web of energy resources, both visible and invisible, that constantly work to keep our lives running smoothly. These resources are as diverse as they are essential, and understanding them can give us a profound appreciation for the energy that surrounds us. Think about the energy resources we rely on. They can be broadly classified into two categories: renewable and non-renewable. Renewable energy resources are those that can be replenished naturally in a short span of time. These include solar power, harnessed from the radiant light and heat from the sun, wind energy, generated by harnessing the wind's kinetic power, and hydroelectric energy, created by converting the potential energy of flowing or falling water. On the other hand, non-renewable energy resources are those that do not replenish in a short period. They take thousands, if not millions of years to form. Examples include coal, formed from ancient plant matter deep within the earth, oil, derived from the remains of marine plants and animals, and natural gas, which is primarily methane and is often found alongside coal and oil deposits. As we navigate through our day, we are constantly interacting with these energy resources. From the electricity that powers our homes to the gasoline that fuels our cars, we are always in touch with the power of these resources. They heat our homes, light our streets, and even charge our smartphones. In this day and age, understanding the sources of our energy and the impact our choices have on these resources is more important than ever. It's about recognizing the immense power that surrounds us every day and harnessing it in a way that is sustainable for our future. Understanding energy resources is the first step to realizing the immense power that surrounds us every day. Now, imagine if we could see the energy around us. What would it look like? Well, one way we can visualize energy is through the concept of radiation. At its core, radiation is simply energy that travels and spreads out. It's like dropping a pebble in a pond and watching the ripples radiate outward. But not all radiation is created equal. Some forms of radiation can alter atoms and molecules, potentially causing damage to cells in organic matter. This is known as ionizing radiation, and it's the type we often associate with nuclear energy or medical procedures like X-rays. On the other hand, non-ionizing radiation doesn't carry enough energy to ionize atoms or molecules. It's the type of radiation we encounter daily in things like radio waves, microwaves, and even visible light. Now, how does radiation interact with matter? That's a great question. When radiation encounters matter, it can be absorbed, reflected, or transmitted. Think of it like sunlight hitting a window. Some of the light is reflected, some is absorbed as heat, and some passes through the glass. The exact interaction depends on the type of radiation and the nature of the matter. But why does this matter? Well, understanding radiation principles is crucial in many fields. Whether it's developing safer medical imaging techniques, improving wireless communication, or studying the cosmos, radiation plays a key role. So, while we can't see radiation with our naked eyes, we can certainly witness its effects. And with the right tools, we can even harness its power. From powering our homes and cities to helping us explore the universe, radiation is a fundamental part of the energy that powers our world. Radiation, in its many forms, is a fundamental part of the energy that powers our world. But how does this energy move around, you might ask? Let's dive into the fascinating world of electromagnetic radiation to find out. Electromagnetic radiation, or EM radiation, is a type of energy that's all around us, permeating the space in different forms. It's like a chameleon of energy, capable of assuming various disguises. Radio waves that carry your favorite tunes, microwaves that heat your leftover pizza, infrared waves that warm the earth, visible light that lets you see the world, ultraviolet rays that give you a summer tan, X-rays that help doctors see inside your body, and gamma rays that originate from nuclear reactions and the most energetic events in the universe. This energy is transported by electromagnetic waves, which are synchronized oscillations of electric and magnetic fields. These fields oscillate in perpendicular planes, moving at the speed of light and carrying energy from one place to another. The amount of energy these waves carry depends on their frequency or wavelength. The higher the frequency or the shorter the wavelength, the more energy the wave carries. That's why gamma rays, which have the highest frequency and the shortest wavelength, are much more energetic and potentially harmful than radio waves, which have the lowest frequency and the longest wavelength. Yet, electromagnetic radiation isn't inherently good or bad. It's how it's used that makes the difference. Used properly, it can cook food, enable communication, provide medical imaging, and even power our homes. But in excess or in the wrong context, it can cause harm, such as skin burns from ultraviolet rays or cell damage from X-rays and gamma rays. So, while we may not see it or even think about it most of the time, electromagnetic radiation is a fundamental part of our world. It's in the light we see, the heat we feel, the music we hear, and so much more. Electromagnetic radiation, though invisible to our eyes, plays a significant role in our daily lives. So, if there are so many types of electromagnetic radiation, how do we tell them apart? The answer lies in the electromagnetic spectrum. It's like a grand sorting hat, placing each type of radiation into its designated category based on its wavelength. Now, picture the electromagnetic spectrum as a long, continuous strip, with radiation types placed along it from the longest wavelength to the shortest. At one end, we have radio waves, the big guys with the longest wavelength and the lowest frequency. These are the waves that bring your favorite radio station to your car's speakers. Next up are microwaves. Despite the name, they're not just for heating up your leftovers. Microwaves are used in radar systems and, of course, in communication technology. Moving along the spectrum, we encounter infrared radiation. This is the stuff that makes heat vision goggles and thermal imaging cameras possible. It's also the reason why you feel warmth when you place your hand near a hot object, even without touching it. Then, we reach the small slice of the spectrum that our eyes can detect: visible light. This is where all the colors of the rainbow live, from red to violet. It's the radiation you're most familiar with, as it allows us to see the world around us. Beyond the visible light, we get into the high-energy end of the spectrum. First up is ultraviolet radiation, the invisible rays responsible for giving you a suntan or, unfortunately, a sunburn. Even further along, we find X-rays, which doctors use to peek inside your body, and gamma rays, the most energetic of all. These guys have the shortest wavelength and the highest frequency, and they're often associated with nuclear reactions and cosmic events. The electromagnetic spectrum is like a roadmap, guiding us through the different types of energy that constantly surround us. Understanding it not only helps us distinguish between different types of radiation, but also underpins many of the technologies we rely on every day. So what have we learned today? We've explored the significance and variety of energy resources that power our everyday lives. We've delved into radiation principles, understanding how energy is transferred. We've examined the role of electromagnetic radiation, a fundamental force in our universe. And finally, we've navigated the electromagnetic spectrum, revealing its organization and incredible diversity. Next time you switch on a light or tune into a radio station, remember the energy and the principles at work behind the scenes. Scene 6. Deep learning and its connection to electromagnetic radiation. Having explored the basics of energy, radiation, and the electromagnetic spectrum, it's time to delve into a fascinating application of this knowledge: deep learning. Deep learning, a subset of machine learning, employs neural networks with multiple layers, and that's what gives it the deep tag. Each layer interprets the input from its predecessor, progressively abstracting the information. You may wonder, how does this tie back to our previous discussion on electromagnetic radiation? Well, consider data in the form of images or videos. They are essentially representations of light, a form of electromagnetic radiation, captured in a digital format. Deep learning models can automatically learn representations from this data, identifying patterns and structures that are often invisible to the human eye. So next time you interact with a face recognition system or a recommendation algorithm, remember the deep learning principles at work and the fundamental role of energy and radiation in making these systems possible. Deep learning, with its ability to learn from vast amounts of data, is a powerful tool in many modern technologies, and it's all underpinned by the principles we've explored today. Our discussion on deep learning and its connection to electromagnetic radiation begs an interesting question. How does deep learning come into play when we're interpreting images? Well, deep learning models can be trained to recognize patterns in images. This pattern recognition can range from identifying objects, classifying images, or even detecting anomalies. The process begins with feeding a large data set of images into the model. The model then learns from these images, identifying common features and patterns. This is particularly useful in the field of remote sensing. Here, we often need to interpret images taken from satellites or drones. These images can provide vital information about the Earth's surface, including changes in vegetation, urban development, and even detecting natural disasters. However, processing and interpreting these images manually can be time-consuming and prone to errors. That's where deep learning steps in. By training a model on a large dataset of images, we can automate the process of image interpretation. The model can quickly identify patterns and features in new images, providing accurate interpretations in a fraction of the time it would take a human. In conclusion, deep learning has revolutionized the field of image interpretation. It has made the process faster, more accurate, and even capable of detecting features that may be missed by the human eye. So the next time you see an image from a satellite or a drone, remember the deep learning principles at work. Interpreting the light, a form of electromagnetic radiation captured in the image, and providing valuable insights about our world. Wow, what a journey we've embarked on together, from the very basics of energy resources to understanding radiation principles and the electromagnetic spectrum. We've even delved into the fascinating world of deep learning and how it can be applied to image interpretation. This journey has not only enlightened us about the science behind these concepts, but it has also given us a glimpse of the future. The convergence of energy, radiation, and deep learning has the potential to revolutionize many fields. For instance, in the energy sector, the use of deep learning can enhance the efficiency and effectiveness of renewable energy technologies. In the field of remote sensing, as we've discussed, deep learning can automate the process of image interpretation, making it faster and more accurate. This could lead to significant breakthroughs in environmental monitoring, urban planning, and disaster management. And this is just the tip of the iceberg. As we continue to advance in these fields, the possibilities are truly endless. Who knows what incredible discoveries await us in the future? So let's keep exploring, keep learning, and keep pushing the boundaries of our knowledge. Because the more we learn, the more we realize how much there is yet to discover. As we wrap up our discussion on energy, radiation, and deep learning, remember that every new discovery starts with a single step of curiosity. So stay curious, stay inspired, and who knows, you might be the one to make the next big breakthrough in these fields. Thank you for joining us on this journey, and we look forward to exploring more fascinating topics with you in the future. I request you to share and subscribe our YouTube channel Quest.